So let's begin day 7 notes. Hopefully you have your note sheet with you. We'll start by looking at graphing complex numbers in the complex plane. Then we'll move on to polar form and rectangular form of complex numbers and converting back and forth. We'll talk about how to multiply and divide complex numbers, usually in their polar form. So let's begin by looking at graphing. We have, with a complex number, a real number portion and an imaginary number portion. So when we graph it, we need a real number line and an imaginary number line. Now the real number line will be the horizontal, the imaginary the vertical. I went and marked off some units along the real number line, labeled 5 and -5, and then 5i and -5i along the imaginary number line. So to plot the W, the real number portion is 4, so I would go over 4 units along the real number line, and then the imaginary number part is -5i, so I will go down 5i units and then put the point and the W, so label that point. And you can do something similar with the INTER. I will let that be up to you. Let's look then at other information regarding complex numbers. Now oftentimes we call the complex number z. So notice it says given z is equal to a or x plus yi. We've called that before a plus bi, but now we're looking more at rectangular, so we'll use x plus yi. We want to find the magnitude or modulus of z, and it's defined as the distance from the origin to a point xy. And it's denoted using the same symbols as we do for absolute value, as the absolute value of z. It follows the definition of absolute value, and that it's a distance from the origin. So we could plot the point x plus yi, like we did up above, call that z. We want to find the distance from the origin to that point. Now to do that, we can draw in our right triangle, drop the perpendicular. So we went x units along the horizontal, y units along the vertical. Now we're not dealing with the I part, that's just telling us that's the imaginary part that we're dealing with. We really want the coefficient. And so to find z, we can go back to our Pythagorean theorem and get the square root of x squared plus y squared. Now keep in mind that when we talk about complex numbers, we also can talk about their conjugate. So the complex number z equals x plus yi has a conjugate, and to find that, we replace the plus with a minus, so we change the sign of the imaginary number part. So the conjugate, which we're going to denote by z bar, is written as x minus yi. Now what will be true is if we were to FOIL x plus yi and x minus yi, those quantities, we would get the absolute value of z. So the another way to define that would be that it's a square root of z times its conjugate, or z bar. Let's convert a complex number from rectangular form, which is z equals x plus yi, to polar form. Now to do that, we have to go back and remember what we talked about earlier in the chapter, that r is equal to the square root of x squared plus y squared, x is equal to r times the cosine of theta, and y is equal to r times the sine of theta. Now we have some restrictions in this situation because we're saying that r is greater than or equal to 0. So we're not dealing with a negative r value, just the positive, and that theta is between 0 and 2 pi, including the 0 but not the 2 pi. Now sometimes when we do our homework tonight, we will be using degrees, and so then we would convert that to theta being between 0 and 360 degrees, including the 0, not including the 360. So if I want to take the complex number z equals x plus yi, and I want to write it in polar form, I have my rectangular form, z equals x plus yi. I know that x is equal to r times the cosine of theta. I know that y is equal to r times the sine of theta, and then times I. Now what I can do there then is factor out r, which we do in polar form, that's how we would write it, and then we would have r is equal, or r times the quantity of cosine theta plus I sine theta. Theta is called the argument of z, and notice that earlier when we defined the absolute value of z, or the magnitude of z, we called that the square root of x squared plus y squared. We know that that is also r, and so the magnitude of z in polar form, or the absolute value of z, is r. So let's look at this first example. We're going to write the complex number 1 minus square root 3i in polar form. And keep in mind we're to express the argument in terms of degrees. Now if x is 1 and y is negative square root 3, we're talking about z being in quadrant 4. We need to take that into consideration when it comes time to do our angle measure. So we're going to start by finding r, plugging into the square root of x squared plus y squared. Watch your notation. That negative square root of 3 should be in parentheses. So we find that r is equal to 2. Now to find theta, we're going to use a tangent function. The tangent of theta would be negative square root 3 over 1, so that gives theta a value of negative 60 degrees. But keep in mind there's a restriction on theta. Theta has to be between 0 and 360, and so we're going to have to convert that negative 60 to 300 degrees. So when we write our answer in polar form, z is equal to 2 times the quantity of cosine 300 plus I sine of 300. Now let's look at converting from complex number in polar form to rectangular form. It would help in this situation to plot the number, so that's how we started. Sketching, I know that r is 2 and that the angle of rotation is 5 pi sixth. That gives me a reference angle of pi sixth and that I'm in quadrant 2. So now I can go and plug in the information I know. So 2 times the quantity, and then I want the cosine of pi sixth, or 5 pi sixths, and that would be negative square root 3 over 2, plus, and then the sine of 5 pi sixths would be 1/2. In order to complete my answer, I need to distribute that 2, so z is equal to negative square root 3 plus I. Now let's look at finding the products and quotients of complex numbers. The formulas that were given deal with two complex numbers, z sub 1 and z sub 2. They are given to us in polar form. Now notice that when we're multiplying them, we are multiplying our r values together and then adding the angles. And then we have our formula for division of z sub 1 divided by z sub 2. There is a restriction, z sub 2 can't be 0. We are dividing our r values and this time subtracting our angle measures. Now those formulas are not given information on a quiz or a test, so you need to know them. Make sure to highlight them or circle them, but go back and study them before you take your quiz or your test. The examples that we have, we're going to do one where we're multiplying z times w, and then we're dividing z by w. We're going to leave our answer in polar form. So z is given to us as 5 minus 5i, and w as 2 square root 3 minus 2i. Now we have our complex numbers, but they're not in polar form. The first thing we have to do then is convert them to polar form. So if you want the extra practice, now would be a time to pause the video and see if you can do those conversions on your own. So let's look at how we would convert z to polar form. If z is equal to 5 minus 5i, that puts z in quadrant 4. To find r sub 1, we have the square root of 5 squared plus negative 5 squared. That gives us r sub 1 being 5 square root 2. To find theta, tangent of theta is negative 5 over 5. That would give us theta being negative 45 degrees. However, remember there's a restriction on theta. It has to fall between 0 and 360 degrees. So theta in this situation would be 315 degrees. And z would equal 5 square root of 2 times the quantity of cosine 315 degrees plus I sine of 315 degrees. In a similar way, we need to find w in polar form. So we know that its coordinates in rectangular form would be 2 square root 3 minus 2i. Again, w would fall in quadrant 4. To find r sub 2, we would take 2 square root of 3, the quantity squared, plus negative 2 squared, and find the square root of their sum. That gives us r sub 2 equaling 4. The tangent of theta would be negative 2 over 2 square root of 3. That gives us theta being negative 30. However, remember that theta has to fall between 0 and 360 degrees, so the theta that we're going to use would be 330 degrees. So W is equal to 4 times the quantity of the cosine 330 degrees plus I sine of 330 degrees. Now let's use that information to find Z times W and Z divided by W. Again, this might be a good time to pause the video and try those on your own to see if you can use the formulas and check your answers when we go through them. So let's look at Z times W. We need to multiply our R values together, so we would have 5 square root of 2 times 4, and then we have that times the quantity of the cosine, and now we're going to add our angle measures together. So the cosine of 315 plus 330 degrees plus I sine of 315 plus 330 degrees. So that would give us 20 square root of 2 times the cosine of 645 degrees plus I sine of 645 degrees. But that's unacceptable because remember, theta has to fall between 0 and 360 degrees. So we have to change that 645 degrees into 285 degrees. So our final answer for Z times W is 20 square root 2 times the quantity of cosine 285 degrees plus I sine of 285 degrees. Looking at that last part then, Z divided by W, we would take 5 square root of 2 and divide it by 4 and multiply that by the quantity of the cosine of 315 minus 330 degrees plus I sine of 315 minus 330 degrees. Now that would give us 5 square root of 2 over 4 times the quantity of cosine negative 15 degrees plus I sine of negative 15 degrees. But remember that theta has to fall between 0 and 360 degrees, so we have to convert that negative 15 degrees to 345 degrees. So our final answer would be Z over W is equal to 5 square root of 2 over 4 times the quantity of the cosine 345 degrees plus I sine 345 degrees. Now hopefully that gives you enough information for you to try your Day 7 homework. I trust that you shall enjoy it, and we can talk about it when we next meet.